Well, hello, AP Chem students. Believe it or not, this is the last section we have to cover. And then we're ready to take that AP test. So this is the last part of unit topic 6 that we have to address. As you can see, it's called Hess's Law. You'll find information about Hess's Law in your textbook, chapter 5, section 6, pages 183 to 186. So the definition of Hess's Law: if a reaction is carried out in a series of steps, the enthalpy for the overall reaction equals the sum of the enthalpy changes for the individual steps. This is not totally a new concept to us. If you think back when we did rate laws, we talked about some reactions that do not occur just in one step. We talked about how there is a series of steps called the reaction mechanism. So it's going to be a similar way to thinking here when you take a look at Hess's Law. So to try and explain it to you, let's take a look at a combustion reaction. So here's a combustion reaction for methane. And as any combustion reaction, we need oxygen. We're going to produce carbon dioxide and water for the combustion of a hydrocarbon. So I was going to show you what we already know and how it relates to what we're about to do here today. So what we worked on earlier this week is we can calculate the enthalpy of the reaction using enthalpies of formation by taking the summation of the enthalpy of formation of the products minus enthalpy of formation of the reactants. And I have it all worked out here, and you can see from the calculations, the enthalpy of reaction here for the combustion of 1 mole of methane is going to be negative 890.7 kilojoules of energy. So that is one way that we learned how to calculate enthalpies of reaction. And we're going to now have to go back and look and see how we can do this using Hess's Law. So we look at the screen and look at the reaction. The combustion of methane is actually a two-step process. The first process, the methane combines with oxygen and forms carbon dioxide and water in the gaseous state. That's step one, and it has an enthalpy of reaction equal to negative 802 kilojoules. So step one in the reaction, methane combines with oxygen, forms CO2 and gaseous water, has an enthalpy of reaction of negative 802. We go back and look at the graph here then. The second step involves carbon dioxide and water reacting, and it turns the gaseous water, converts into liquid water. So there's an equation representing step 2. So the enthalpy of reaction for step 2 is negative 88 kilojoules of energy. So this is a two-step reaction. Now here's what Hess's Law states. Hess's Law states that the overall enthalpy of a reaction is equal to the enthalpy, the sum of the enthalpies of the series of reactions that lead up to that overall reaction. So this is going to bring back something else we worked on earlier this year, and that is where we add equations. We did this when we worked with equilibrium expressions. So here's how Hess's Law ties into enthalpy. So there's step 1 from the reaction shown up here, and then here's step 2 in the combustion of methane. So as we've done previously, if you have something on the left side of the equation, on the right side of the equation, we can cancel it out. So we cancel them out, and according to Hess's Law, enthalpy of the reaction is going to equal the heating reaction of reaction 1 plus 2. It comes out to equal negative 890. And that is what we had in the previous example we just worked out using enthalpies of formation. So we can figure out the enthalpy of reaction by using enthalpies of formation, or if we are given the enthalpies of reaction of a series of steps to lead up to an overall reaction, we can add them and come up with the value here as well. Now, I just want to draw to your attention, you may remember doing similar things like this when we did equilibrium. When we did equilibrium, we multiplied the K values, and if we had a flipped equation, we would take the inverse of that. This is similar, but it is a little bit different. With Hess's Law, we're going to talk about adding the H values. We're not multiplying here. So how about we take a look at another example. So here's an example. We're going to have solid carbon reacting with water, gaseous water, and it'll produce carbon monoxide and hydrogen gas. We are asked to calculate the enthalpy of reaction for the reaction right here using these equations. So we are not going to solve this using enthalpies of formation. We're going to solve it using Hess's Law. Now, what I've done here is I've colored everything involved in the reaction red. These are the things we want in our final reaction. So this is like a puzzle, and we did these before earlier in the year when we did the equilibrium expressions K. Now recall that we're allowed to flip equations, and we can multiply the equations by a whole number or a fraction, whatever we need to do to make this work for us. So to start off, we have carbon as a reactant, and this equation is carbon as a reactant. So I don't think we want to mess with this. We're going to leave this equation just the way that it is. 1 mole of carbon, 1 mole of carbon. I'm going to switch my focus to gaseous water. Now you can see that we want the water to be on the reactant side. What they're giving us here is water on the product side. So that's indicating to me that we're going to need to flip this equation. We need to put the water on the reactant side, and H2O2 are going to become the product side. So we, in essence, are going to flip this equation. When we flip the equation, I want to draw to your attention that we're going to also have to change the sign from negative to positive. Something else I want to point out is we need 1 mole of water, and this equation gives us 2 moles of water. So we're probably going to have to go ahead and flip this equation, and we're going to have to also multiply it by 1/2. So this equation here, if I multiply by half, I'll have 1 mole of H2, half a mole of O2, 1 mole of H2, and we're going to flip that. So we're going to put these on the product side, and the H2O becomes on the reactant side. Let's continue to analyze the equation. You can see the end equation, we want 1 mole of CO as a product. Again, we're given the equation with CO as a reactant. So just like the previous example, this equation here must be multiplied by 1/2 to give us 1 mole of CO. And we've got to flip this equation to put the CO on the product side. We want CO on the product side. So if I write that down, it's going to look like this. Left the first equation just the way it was. The second equation, I multiply by half. So 2 times 1/2 is 1. So we have 1 CO2, 1 CO, and half an O2. We're flipping this equation as well. That brings water over onto the reactant side. 1/2 times 2 gives us 1 mole of water. 1/2 times 2 gives us 1 mole of H2. And then 1/2 times 1 gives us 1/2 of a mole of oxygen. So if we multiply the equation by 1/2, we have to also multiply the enthalpy of reactions by 1/2 as well. So if you take a minute here and pause and look at what we have done, we flipped this equation. This equation was flipped, as shown here. We had CO on the reactant side, it's now on the product side. And we multiplied by 1/2, so we have just 1 mole of CO. We did the same thing to the second equation, and we're going to take that into account over here by multiplying the enthalpy of reaction for that step 3 by 1/2. And we made the negative 483, the negative 566, we made positive because we flipped the equation. So when equations are flipped, the sign of delta H must be switched. So if it's negative, you're going to make it positive. If it's positive, you're going to have to make it negative. And that stands to reason, because if something is exothermic, if we reverse that process, it's become an endothermic reaction. So the final answer for this, I worked on the math down here. 1/2 times 566 is 283. Half times 43.6 is 241.8. I added them up, and the enthalpy reaction for this is 131.3 kilojoules. In this case, it's going to be positive. That is how we do Hess's law. It's like a puzzle, so you don't get frustrated. You just got to ease into a little bit, and the more you do, I think the more comfortable you can get with these, and the easier they'll get for you. So again, try to recall doing this when we worked with equilibrium constant K, where we went ahead and we flipped the equations and we also added them there. Well, as they say in the Looney Tunes, that's all, folks. So I'll post this video up, and if you have questions, you can always contact me through Google Hangouts. You know my office hours, and you can always email me. Okay, everybody, take care.